Today's lesson is on bits and bytes. The number system that you use, been using for many years is the decimal system. It's also called base 10. Okay, it's called base 10 because there are 10 digits. 0 through 9 is our 10 digits. So we're going to go ahead and convert the number 9. We're going to look at the number 9047 and understand, hopefully, what the base is in base 10, and also how we get the number 9047. The first place to the right, the number 7, okay, you learned way back in elementary school, is called the ones place. Okay, that ones place, the number 1 comes from the fact that that ones place is equal to 10 to the 0 power. 10 to the 0 is equal to 1. So we take the digit 7, we multiply by the 1 in the ones place, and then we get the fact that that one's worth a 7. The number in the next place is the number digit 4. That's in what you learn as the tens place. Well, tens place is 10 to the 1, it gives you 10. So 4 times the value of 10 gives you 40. So that particular number, that digit 40 gives you, 4 is worth 40. The next digit, the hundreds place, has a value of 0, okay, which is 10 squared. 0 times 100, it gives you 0. So that digit is worth 0. The fourth digit number 9, is the thousands place. 1,000 is 10 to the third, so that's worth 9,000. Okay, so we add those up. 9,040 plus 7, we get 9,047. Now let's relate that to the binary number system. Binary number system is a base 2 system. We call it base 2 because there are 2 digits, both 0 and 1. So right now we're going to take a look at the binary number 1011. Now this base system, okay, when we're doing decimal is base 10. Well, binary is base 2, so instead of a 10 to the 0 power, in this case we're going to have 2 to the 0 power. So 2 to the 0 gives us 1. So this digit in the first column is worth 1, so 1 times 1 gives us a value of 1, so that digit is worth a 1. Well, the next column is 2 to the first power, which is 2. 2 times 1 gives us 2, so that digit is worth a 2. The next column is worth 2 squared, which is 4. All right. 0 times 4 is 0, so this place is worth 0. The next digit is worth 2 to the third, which is 8. 1 times 8 gives us a value of 8. Now we add up all of the values. 8 plus 0 is 8, plus 2 is 10, plus 1 gives us 11. So that's how we convert 1011 in binary to 11 in decimal. Now let's relate that to another number system, which is the hexadecimal number system. Hexadecimal number system is base 16. If you recall, a hexagon has 6 sides, so hex is referring to 6. Decimal, we said, is referring to 10. The prefix deci we use in terms of decade, right? Okay, decades have 10 years in it. So hexadecimal is 6 plus 10, which is 16. The base 16 has 16 digits. The digits 0 through 9 are the first 10. After that, we run out of digits, so then we go ahead and continue working with letters. So after 9, we go to A, B, C, D, E, F, and that gives us a total of 16 digits, which is base 16. So right now we're going to take a look at the hexadecimal number 3A, and we're going to try and convert that to decimal. A happens to be worth 10. As we said, after the 9th digit, or after 0 through 9, the next one is going to be worth A. Next digit is A, which is worth 10. The first digit is 16 to the 0 power. 16 to the 0 is 1. Okay, so the value of the digit A is 10. So 10 times 1 gives us 10. So this particular value is worth 10. The next place is 16 to the first power. Again, our base is 16. 16 to the first power is 16. So that this particular digit is worth 16. Well, we got 3 of them, so 3 times 16 gives us 48. So now in order to calculate what the equivalent of 3A is in decimal, we take 48 and we add 10 to it. We get 58. So 3A in hexadecimal is equal to 58 in terms of decimal. Hexadecimal as well as binary numbers are very often used to represent colors. There's one way we can represent colors is what we call an RGB value. That RGB value is made up of three different numbers. Okay, the first number is telling us how much red there is. Then the second number how much blue there is, and then the third number is how much green that there is. So the primary colors are red. So red would have all red, which is 255. All of the numbers have to vary or are always vary somewhere between 0 to 255, which represents 1 byte or 8 digits. Okay, a red would have no green and no blue, which is why we have 25500. Green would have no red, would have all green, 255, and would also have 0 blue. Blue would have no red or green, so 00, and then the last number would be 255. Secondary colors are where we're combining two different ones. If we take red and blue together, okay, we're adding all of the red and all of the blue, but no green, we're going to get magenta. As you know, if you remember from elementary school, red plus blue gives you purple. In this case, magenta is kind of like purple. Cyan is kind of like blue-green. Okay, so cyan is going to have all the blue and all the green and no red. Yellow, if you remember from elementary school, is a combination of both red and green. So 255, 255, is going to give us yellow. We also use binary numbers to represent the amount of bytes. For example, bytes when we're buying memory, let's say for a computer. If you're buying a computer that has 16 gigabytes of memory, well, those bytes ultimately are a number that is derived from a binary number system in terms of bytes. Hard drives that are on computers are also bought and sold in terms of bytes, much larger numbers such as, let's say, 1 terabyte drive, 2 terabyte drive, 4 terabyte drive. Okay, but again, it has to do with bytes, which ultimately is a binary number. The way a hard drive actually saves information is it uses this device, which is called a hard drive head, and on the end here is a somewhere on here is a magnet. Okay, and this magnet can either magnetize or demagnetize the actual platter on the hard drive. You'll see there's actually 1, 2, 3, 4 of these actual fingers that are kind of sticking out here. It can actually save on multiple platters at one time, each of those saving on a different platter. So when you're writing or reading bits, again, bits are binary numbers, either zeros or ones, to a hard drive. The actual hard drive here spins around in circles, and this head moves back and forth, and it reads or writes the zeros and ones, and then it goes ahead and interprets those to see what actually information, let's say what program is being opened up or what program is being saved onto the hard drive. When you're actually physically writing the actual bits, again, this is an example of a hardware abstraction where we're not seeing all of this, but this is what's going on. There's two ways that you can actually write data to the hard drive. One is called a ring writing element, and this uses what we call longitudinal recording. This is a standard way of saving information on a hard drive. What it does is it records either a north or south, and the north and south are represented by these arrows. So let's say if one of these, maybe this one to the left is north, so then this other one pointing to the right would be south. So here we'd have another north, north. One of those would be ones and one of those would be zeros. So we're using the actual write head on our on the hard drive head to go ahead and save ones or zeros in the forms of either north or south in terms of the way that it's written on your hard drive. That's why for your hard drive, if you ever expose your hard drive to magnets, that can damage your hard drive. Another way of saving data on your hard drive is what's called a monopole writing element, and that instead of longitudinal recording, it uses perpendicular recording so that the actual north and south arrows are not horizontal, they're actually vertical. They're running up and down on this recording layer. Again, both of these are different ways of saving information on a hard drive. But again, because of hardware abstraction, we don't really need to understand what's going on at this level. We just know that when we save something that it gets saved on the hard drive.